So today we're going to talk about, yesterday we talked about ionic compounds and the properties of ionic compounds. Today we're going to talk about molecular compounds, of course. Molecular compounds are non-metallic atoms combined together. They're held together by covalent bonds. That's important for us, covalent bonds that are formed, and covalent bonds basically implies that we're going to be sharing electrons, yes? So we're sharing electrons between atoms, okay? The covalent bonds will occur within the molecule and are very strong. The forces that act within the molecule are called intramolecular forces. Okay, make sure you know that. Intramolecular forces. The attraction between molecules is much weaker. They're known as intermolecular forces. So between molecules are intermolecular forces. And I'll give you an example of what we're talking about here. In fact, we're going to use water as our example again, is probably just fine. All right. Good. I think we have all that, yes. In the space below, sketch the difference between intra and inter. I might actually have that here, I think. So intramolecular is, we're just going to chop this. This is actually an H right here. We're going to chop it off right here. So that's an H right there, and this is an H here, of course. This is an example of intramolecular. So we're talking about intra, what holds this one molecule together. Okay, that's intramolecular, intra. And we're going to just stop right. Like I said, intramolecular forces are fairly strong, probably not on the same level as ionic, right? But fairly strong. But when we talk about molecular compounds, they have specific shapes. In other words, they have specific types of molecules, right? In this case, we got two hydrogens and oxygen. They've combined together. They're sharing those electrons. Yes, not equally. It doesn't matter, but they're sharing electrons there, and that's somewhat strong. Okay. The issue now, though, is this. Look, if you just had one water molecule, you'd probably never see it. Yes, because water, that'd be incredibly small. So we have billions and trillions and billions of them. That's a made-up number, by the way. We have lots of water molecules. And how do we get to see water? Well, they have this bond. They have this force that acts between molecules. Okay, so one links. You can't see individual molecules of water, but you can see, I'm going to go with a billion of them. Okay, because this one is linked to this one, to this one, to this one, et cetera, et cetera. And there's enough of those linking that holds them together that you can see water. Okay, and that's how we, and then in ice form, of course, they're all kind of locked in together. We've taken away enough energy where they don't have any energy to move, kind of thing. Okay, we call that kinetic energy. So this is somewhat strong. This is intra. In this case here, we call this covalent bonding, yes? Okay. However, that's only one water molecule. How do we get a water linked to another water? Well, that's something called intermolecular forces, and now we'd be looking at this side here. Okay, so this is the force we're talking about. I don't have yellow, but this is the force we're talking about here, the link between molecules. Okay, that's intermolecular forces. Between molecules. Now, this is what we call an so between water molecules. This is responsible for states, basically. All right. So in gas form, okay. Well, let's start in solid form. In solid form, so we'll use water as an example. At about 0 degrees Celsius, right? This intermolecular force, because water, of course, when we talk about kinetic energy, we talk about how fast they move. Yes, these particles move. So when we cool the water down to 0 degrees Celsius, we cool them down to enough so that this bond right here, this intermolecular force, is strong enough to hold them together. Yes? So what's happening is that it's cooled down enough. They're not moving very fast. So they've cooled down enough to hold those two things together. And that's how we get ice, of course. If we put a little bit of energy into that, of course, we change it from the solid state to the liquid state. And what happens is we start to break some of these bonds here. So we break some of them, but not all of them. All right? We break some of them, not all of them, and they start to kind of move back and forth like this. Okay? They have a little bit more energy, so they want to move, but they're still kind of caught still kind of attracted to each other, basically. All right. And if we heat up water to 100, of course, then what happens is we actually break almost all of those bonds and we get individual molecules of water. Okay. Because now we've given them so much energy. When we heat up substances, we give them energy, that kinetic energy. You've heard that before probably at some point. And they start to go so fast that that bond between them can't hold on anymore, right? And so then they are free to go into gas form, basically. All right? So that's kind of in intermolecular forces when we talk about those. And there's three main ones that we'll talk about next year. But the three main ones are hydrogen bonding, which this happens to be an example of, hydrogen bonding, dipole-dipole, and London forces. And they're ranked kind of differently. It depends on what they are, but they're not super strong, all right? They're not super strong. They're pretty weak, comparatively speaking. Water, okay, water's pretty unique, actually, but water boils at 100 degrees Celsius, right? It melts at 0, to give you kind of a perspective here, yes? So it melts at 0. What do ionic compounds melt at? 800 and up-ish, right? Give or take some thousands, right? But 800 is kind of where I'd say they start, give or take a little bit. They start at 800, okay? This is a molecular compound. It melts at 0. All right, that's the difference we're talking about here. It's substantial. All right, it turns out that these, like I said, these intermolecular forces are not particularly strong. Okay, even if it is water is pretty unique, it's one of the strongest ones we have. But luckily for us, it doesn't boil it doesn't boil till 100. All right. But that's the difference between intra and inter. Inter is between. If you have like a intermale, it's between, like, people, right? Between places. Intra, I guess if you're looking for, if you're an introvert, you kind of stick to yourself, yes? And so that'd be like the Mr. Bachek right there of the water molecules. That's, you can laugh. It's funny. It's okay. What do you call a fish with no eyes? No way. Okay. All right. I'll explain it to you. A fish with no eyes. No, it's not. No, it's a Mr. Bachek joke. Okay. What's next here? Melting points. So I don't know. What do we got to copy here? Well, melting points, like we just talked about, actually, like I had a little premonition there. In molecular compounds, only a small amount of energy is required them to cause the molecules to move apart from one another, break the intermolecular forces, right? Causing the compound to melt. When this occurs, the compound melts. Not a lot of energy is required because the force attraction between molecules is weak. When a molecular compound melts, the molecule itself does not break down. So that's important, right? When a molecular compound melts, we're not breaking down the compound. We're not breaking down water. We're not breaking into hydrogens, oxygens. We're just changing the states. We're breaking those intermolecular forces. Okay. Is that all right? Okay. So it doesn't break down. It just basically changes form. It changes from solid liquid to gas. Basically, that's a prime example there. All right, we break enough of those intermolecular forces. Now, if you had a gas and you continued to heat it, and were able to superheat it, etc., you might eventually get to hydrogen and oxygen, but that's a decomposition reaction. That's not this. That's something totally different. All right, moving on. A molecule is neutral. It is neutral because it does not have an overall charge, even when it's dissolved in water. Because of this, a molecular compound will not conduct electricity as a solid or as a solution. By the way, this is exactly what a conductivity tester looks like, which you're going to be using in the lab. It basically just has a 9-volt battery on it, and it's got a light. Ours has a scale from 1 to 10, and 10 are, of course, very conductive, and 1's not very conductive. And if it doesn't light up, it's either broken or it technically should be a molecular compound, technically. Now, having said that, we'll talk a little bit about water coming up here when the time comes, but water is able to conduct a little bit of electricity at times. And the water that we use here is pretty good, but it's not perfect, okay? And even if we had pure water, which we don't, even that still conducts a little bit of electricity at times, and there's a reason for that. Okay, good. Weak crystal shape. So crystals of molecular compounds crumble easily because the attraction between molecules is weaker than the attraction between ions in a molecular, between ions. So basically they're saying that kind of reads a little wordy there, but it still has a crystal shape, but it's not nearly as strong as the ionic shape, okay? So that's basically what they're saying there, okay? Do we need anything else there? Nope, we're good. Okay, now solubility is a little tricky with molecular compounds. Some molecular compounds are soluble in water, like sugar, while others are not, like wax or oil. I'll just let you copy the rest of that there. Now, yeah, so this is where it gets a little tricky. Just like ionic compounds have different degrees of solubility, so do molecular compounds. So if you took a solid of an ionic compound, you put it into water, it will always dissolve a little bit, but it may be aqueous or solid, yes, like we did on the chart the other day. It might completely disappear, or you might see a little bit of solid at the bottom, and it might be very, very cloudy kind of thing. So we have those kind of options, or it might just sink to the bottom. You might see the solid at the bottom. That's what can happen with ionic compounds. Molecular compounds are kind of the same in that regard. So it's not easy to tell the difference between them sometimes because, like I said, they kind of act the same. Some compounds dissolve very easily in water, and some do not. Right? And I'm going to give you a little example here, but what it really depends on, of course, is water. Water is polar. We know that, yes? Water, if you wanted to draw this, would be a little bit of negative and a little bit of positive and a little bit of positive, okay? Now, along comes a molecular compound. And if that molecular compound is non-polar, let's go with polar first maybe, okay? So if that molecular compound turns out to be polar, which you're not really gonna know, okay, at this point, but I don't know, let's say it's, well, do I wanna go there? I don't know. You know what, I'm just gonna go with this. Let's just keep it simple for you guys. If I put some sugar into water, sugar turns out to be polar as well. In other words, it has some negative ends and positive ends to it as well. So what happens is, because it has, I don't know, I'm just gonna put some negative end and positive end kind of thing. So because it is a polar compound, and again, you're not gonna know this, which ones are polar and non-polar yet. That's probably a next year thing. But if there's a negative end and a positive end, then these two ends attract each other, and they will pull the compounds apart from each other. In other words, they will dissolve, basically. All right? So that's what it kind of depends on. That's what solubility of molecular compounds depends on, whether the compound is polar or non-polar. If it's polar, that means it also has a negative, a little bit of a negative end, a little bit of positive end. Water likes that, so water will pull it apart. If it doesn't have a negative end and a positive end, for example, like they gave you an example of oil or wax. Wax is, I believe, if I'm not mistaken, C25H52, okay, which is a nonpolar compound. It doesn't really have that negative and positive end to it, and therefore it will not dissolve in water. Okay, and that's really what molecular compounds, that's how they decide if they're going to break up or not. Unfortunately, you don't know these compounds if they're polar or non-polar. So that's not really going to help you lab day. But we have other tests for that. What's the biggest difference between, what do you think the biggest difference is between ionic and molecular? I think we already talked about it today and last day. Well, in terms of whatever. whatever you want to pick. What's the biggest difference between ionic and molecular as far as properties goes? Yep. Yep, that's the biggest one. Okay, and that's the easiest one for us to test as well. Another good one would be, of course, probably what? Melting point. But we're not going to trust you with that because we don't have 800 degrees Celsius. So, right? So that'd be a little tough. But obviously, if you're, if you're trying to melt a molecular compound and melts right away, then you'd probably know. If it doesn't melt until you get to like 100 or 200, then we probably could call it a day and say probably ionic, probably. But regardless, anyway. Okay. Now we're going to talk about acids, and we're going to do a whole lesson on this because you're AP, so you get the whole lesson on acids. That's tomorrow, I guess, ish. But acids, according to Arrhenius, which was just a guy who was doing a lot of theories and definitions about acids and bases back in the day. Acids release hydrogen ions when dissolved in water. So we still kind of use this definition today. We've since modified it a little bit, but we still kind of go with that just for simplicity's sake, and that's kind of where we're at right now. So for example, hydrochloric acid. Now, I should probably have that there. Do you have that there? Okay, let's write that equation down there, please. So here's an example here. The first thing we talk about probably is if we go back to, I think it was yesterday, we went over the homework questions, right? And somebody asked, why isn't it hydrogen monochloride or whatever the case might be? And the answer is, well, because when we talk about hydrogen being out front here, okay, like so, when we talk about that, we normally name it as an ionic compound. So we just call it, in this case, that we'd call this hydrogen chloride. Because, okay, we're going to, usually what we say is, okay, well, this is hydrogen chloride. I'll give you another example after this one, but this is hydrogen chloride. And if we put this into water, what will happen is water will pull this compound apart and we'll actually make these two ions instead. So we get the hydrogen ion and the chloride ion. That's what this basically means. So if you take hydrogen chloride, it's actually a gas. Okay? Hydrogen chloride starts out as a gas. And it kind of looks like we share electrons, by the way, and if you wanted to get into details here, it would look a little something like this here. All right, that's what hydrogen chloride looks like. It's a molecular compound, hydrogen and chlorines, okay? Hydrogen chlorine. Along comes water, so as soon as you put this, hydrogen chloride gas is not very dangerous. It is a gas. It's not dangerous as long as, and here's the trick, as long as there is no water. But there always is, right? So there's water in the air, there's water in your hands and things like that. So, but if you just had hydrogen chloride gas, as long as there's no water, it doesn't turn to acid. This is just a molecular compound. It'd be neutral, it wouldn't have a charge. It's just a molecular compound, like any other molecular compound. It would be no different than a water compound kind of thing. But as soon as you put it into the presence of some water, so as soon as some water comes along, again, we have this negative end and this positive end. And this, by the way, this compound is polar as well. Okay, it's got a positive end and a negative end. And these two attract each other. And what happens is water now splits this compound apart. Okay. So what happens is we get this, H plus, and we get some Cl minus ions, just like we have here, all right? As soon as we get the H plus ions, we call those hydrogen ions, that is the response, that is an acid now, okay? That's what makes it an acid. So this right here, these H plus ions, these hydrogen ions right here are acids. That's what makes an acid. All right, that's the responsibility. Well, that's the property of H plus. Gives us acids. What do you know about acids? Give me a couple things. Yep. Yep, they cause corrosion. What else? What else do you know about that? Yep. They can. What else? pH. Tell me something about pH. Huh? Yep. Okay. Yeah, so they're lower than 7. Yes, 7's neutral. What else? Yep. Well, 1 to 6.99, I guess. Actually, not true at all. They go below 0. Okay, so that's the scale is just a rough scale. 7's neutral. Anything below there is considered an acid, and it goes down. We have acid here; it's -2. Right? Don't screw around in class, or we'll take you there. Okay? No, I'm just kidding. We can't. No, I can't record that actually. Too late. Just kidding. No. But it doesn't have to stop at 0 or 1 or whatever. It goes below that, just like bases go above 14 as well. We'll talk about that. That's not important. Okay. pH less than 7, right? The responsibility comes from right here. That's what makes that an acid. All right. You don't have to copy this one down, but I'll just show you one more here, right, real quick here. This one here is HNO3. Now I don't know what state it is in to start with. Actually, I would say it's probably a liquid. And when we put it into water, so when we dump this into a bucket of water here, okay, we will get H plus and NO3 minus, hydrogen nitrate. Yes, is what we would call this, by the way, hydrogen. We're going to do naming tomorrow, hydrogen nitrate, and that would be aqueous and aqueous. Again, it has H plus ion, so that's what makes it an acid, yes? Okay. Why does a pH meter work in all acids? Well, because all acids have H plus, right? Right? So that's why pH, you can put pH in hydrochloric acid. This is nitric acid. We'll learn that tomorrow. Sulfurous acid, carbonic acid, right? It always works. It always registers because they're always measuring the same thing, which is the hydrogen ions. Turns out this really does, I really don't care too much about that. I mean, that's how we name it, but we don't really care too much about that because what we're interested in here is the acid part, which is the hydrogen ion. And all acids have hydrogen ion when you put them into water. Now, good? I kind of got off a little topic there, but nonetheless, you're AP, so you have to. Some examples of acids here. Acids tend to contain hydrogen on the left-hand side of the formula, so you'll see quite a few examples here. Whoops, let's go back to here for a second. So here's H2SO4, for example. Sulfuric acid. What's another one here that they have? We did nitric acid. Here's phosphoric acid would be that case there. By the way, these formulas come from the fact that we have H is a 1 plus and SO4 is a 2 minus. Notice how we're basically pretending that they're ionic compounds, yes? Okay, even though they're a bunch of nonmetals, hydrogen, sulfur, and oxygen, when they combine together and you put them into water, we get this kind of separation of ions, okay? So they have this ability to, I guess we should say, use the proper term, ionize, okay? Phosphoric acid comes from the fact that this is H is a 1 plus and PO4 is a 3 minus, okay? Swap and drop. What's the last one here? And then, so now it says here, acids tend to contain hydrogen on the left-hand side of the formula, or this. And this is all important stuff I'm telling you here, because this is gonna be your lab here coming up. If you get something like this, all right? The reason they do this is because if you were actually to draw out this compound, this is how you would draw it. You'd have a carbon with 3 hydrogens around it. You'd have another carbon combined to an oxygen to combine to an oxygen with a hydrogen. Okay, that's why they draw it out like this. Okay. You may also, by the way, what you're looking for here is this COOH group here. Okay. Also, acid. Okay, so keep that in mind. If you see this, that also could be an acid, COOH, right? So make sure you keep that in mind. Sometimes, okay, basically where this comes from, this is hydrogen acetate. Otherwise, does anybody know what this is called? Hydrogen acetate. Sounds a little bit like something. You can go to Costco and buy it. Yep. Yeah. Yeah. Vinegar, acetic acid, yes. That's what this is. This is a weak acid, and I don't know about you, but I put it on French fries, yes? Right? French fries, or if you have the hiccups, you would drink a tablespoon of this, and it'll get rid of them guaranteed. 100%, 90% of the time works all the time, 60% of the time. I don't know what that means. Yeah, seriously though, vinegar, it always works, all guaranteed. You may see it written like this at times, okay, as well. And that's where the hydrogen, and this is called the acetate ion from the top left periodic table, hydrogen acetate, all right? But sometimes, like I said, it can be written either way, but that's also indicative of an acid, all right? Good, I think we're gonna stop there for today. And I guess we don't have any homework. You guys can always review, eh? Don't be shy.